2017. And it started in June, and it's kind of a rolling program, so if anybody is interested in that program or knows a startup or a team that is interested, you can check us out at us.techcode.com. If anyone is interested in office space, we also have that, so feel free to contact us for any of that. And then the space, we do tons of events, and we really like to, just be in the community and get to know people and have people here and, share their awesome meetups and stuff like that. So again, if you know anybody who's interested in event space or any of that, feel free to let us know, and welcome again, and thanks for being here.
Thank you.
Awesome. Thanks, guys.
Do you have an introduction on your slide?
Yeah.
Okay. So, in that case, I won't say.
All right.
But yeah, I heard this talk, at least twice, and it was. It's an awesome framework, and I think it filled a hole in the ecosystems. So we plan to use it. We have a project plan laid it out. So without further ado, and I can introduce himself, and he's from Uber, and the rest of you can help from the slides. Thank you.
Thank you. Thanks a lot. Thanks for having me. Hello, everyone. Thanks for taking the time to come and attend the talk. So, my name is Vinod, and I had the good fortune of being one of the early members of the data team at Uber. So, built a lot of our foundational systems there. Previously, I was at LinkedIn working on Voldemort, if you heard about it, that's LinkedIn's Cassandra. And before that, I have background in database replication. So pretty much I worked on data infra projects for the past 10 years. Okay, so today I'll introduce Hoodie, which is open source incremental processing framework. And first of all, we'll go into the problems that motivated us to build this, and as well as a deeper sort of understanding about the concepts behind Hoodie and stream processing, batch processing, then what is incremental processing, those type of stuff. Then we will go to a deep dive of what we are actually doing under the hood, talk about use cases, compare it with other systems out there, and see what the trade-offs that we picked. And then generally it's open source. We open source this in February. We have a small budding community of contributors, and where we hang out in a Slack channel, and we are trying to drive the direction forward. So we'll also talk about where we are on that and how you can get involved if this is something that interests you. So overall, like I think everyone else, a lot of companies, so we use a combination of Presto, Spark, Hive, Presto for analytics, interactive queries, Spark to do a lot of your machine learning applications, safety applications, whatnot, and then Hive for your standard ETL, or the Hive is the whole workhorse which just gets your queries done, right? So SQL kind of pipelines running on Hive. Across all of this, what we had is a real need for faster data, which comes basically from the nature of Uber's business. There is always like an upside to having the most recent data in our data lake, and that's primarily where we started from. And this problem for us, a very real problem that kind of forced us to think very hardly, is our primary ingestion of a trips database. So trips is, as you can guess, is a very primary data set for Uber, and the sort of problems that we saw here in terms of ingesting this data set into Hive as a Parquet data set was the beginnings of why we started thinking about this. So, to be very specific, what we had was, we used to run a job every 30 minutes, but every 30 minutes we would get new trips as well as updates that were happening to older trips. So these updates result from, say, we used one card, but we had to update the other card, or some payment method update, or the rating got updated, or some rows were added when the trip was originated. Then there were other later information the actual time it took for the route from the initial estimate time, blah, blah, blah. So the trip object mutates over its life cycle. And what happened here was we had a big amplification factor. There were a lot of updates going back into the past. Like you can see even like 1 year or even 1 year into the past. Right? This is, I'll give you an example. If you took an Uber here and then you never take an Uber again for the next month, the next time you open the app, it's going to prompt you to rate your last trip, no matter what. So if you now add the feedback for your old trip, it comes here and as the the rating for the trip. So this is like one example, but fundamentally we said, oh yeah, we need to deal with updates here. None of the standard tricks that people usually do, which is bulk update, like bulk loading the table or rewriting partitions alone, kind of worked for us because the spread was just too high. So we actually we didn't build Hoodie right away. We just did what everyone else does, which is you have a database, then you somehow manage to scrape the logs into something like Kafka. Then you have another database which can now take the updates. So in our case, this is HBase, which was close, which was just working directly off of the same HDFS cluster, and we simply, replicate these strips one-to-one here, and then periodically a job essentially dumps this entire kind of data into a columnar format like Parquet, so that we can have, analytical queries that can run on this. So then it doesn't stop from at that, right? You usually have derived tables which are built off of this, and the standard way the batch world works is, oh, this changes, and then the derived tables are batch recomputed. So the problem here is, as you can see, it's a very large data set, and no one's able to fully batch recompute. So people start making assumptions like, I'm going to assume the fare was not adjusted, not more than like 7 days, 3 days, like, basically very ad hoc sort of business rule assumptions. And then these tables end up becoming approximation. So from a user standpoint, if you're querying this through Presto, you neither have, in some cases you don't have accuracy, in some cases you have anyway very large latency. And it didn't even stop at that, right? So we grew. So we kept throwing hardware at the problem. We'd gone all the way up to 1,000 executors. And this is, I think, right about 500 executors is when we really started to think about, hey, this is not going to work, right? And our brainstorming process was something like this. Why don't we just query HBase? Okay, all the data is there. It's there like, almost real time. So why not do this, right? But the thing is, HBase is a OLTP database, end of the day. So it's a bad fit for scans, and it does not have any support for nested data, which things like ORC or Parquet have. And there is a significant operational load to managing a HBase cluster. So what I mean by this is, if you want all of your Hive queries for your primary data set, like say something like trips at Uber, to be handled in a scalable way, you should prepare for operating HBase at the scale of HDFS, right? Because it's going to have to take the same kind of scan and RPC workload on the HBase region servers. Then we thought about what the next logical step that most people think about. It's like, oh, why don't we bring in this specialized analytical database which supports updates or has like in-memory. There are teams still, like we have use cases where we are doing that, but this particular use case, like this is a heavy, we are trying to build the foundational data lake for Uber, which means we have to be able to cross-join trips with, say, some other Kafka stream that a product engineer kind of comes up with, right? So our problem here is, if we move this alone into a specialized database, we can't, move all of our Hadoop data into these specialized databases. And now we anyway have to think about this kind of federation or merge layer, and that's again going to be a hard thing. And we'll have Lambda architecture, we'll have to keep copying data back and forth, and we anyway need to solve that problem, because if you're doing Lambda architecture, if you need to backfill the analytical database, we need to come back to Hadoop, and we have to solve this problem here, right? The other kind of things is, this one's really good. This one's basically saying don't solve it. It is, hey, don't support snapshots of the trip table at all. Just support logs. And we also tried this a little bit, although I was not a big fan of this. I mean, logs need to be compacted anyway. Logs are great, but they're great if there are inserts. If they're say Kafka events which don't relate to each other, then sure. But if a database log needs to be compacted at some point, otherwise when you're reading, your reads become increasingly more expensive all the time, right? And if you leave it to the users, the merging is done multiple times. So every downstream consumer reading this will merge once, for each of their jobs. And also they will do it very inconsistently, like what I was saying before. So end of the day, we don't have good source of truth for a lot of these data sets, and that's a big problem. And generally we talked about, okay, can we data model it differently? But essentially it turns out it's a fundamental problem. If far changes, yeah, something has to change downstream, and none of this changes the fundamental nature of the problem itself. So then we got to thinking, okay, what is the missing gap? So we have a Hadoop data lake right now, and it already stores petabytes of data. What is the gap here that we need to fill to be able to just keep things as it is? The users don't see any difference, but they have fresher data. So to solve this, we actually, it's a very well understood problem in the OLTP, the RDBMS land. So typically, if you look at traditionally Oracle replication, MySQL replication, essentially you have changes coming to a table. Then you usually have a redo log from which you can pull these changes. You do whatever transformation that you want to do, and then write it back into another thing, right? So this is pretty much pretty much the same problem. If we can update this guy, the first trips table, and then somehow efficiently let the downstream job know that these are the only changes from the upstream table, then that's essentially seemed like what we needed to do was come up with something like this. Except now we have columnar file formats, and these are not OLTP workloads, these are read-heavy analytical workloads, so the choices for indexing and those kinds of things will change a lot. And then we are doing this not in a single server, but petabytes of data and thousands of servers, right? But ultimately our answer was, yeah, we need to do some kind of upserts, and then we need to have an efficient way of getting incrementals from a database, data set. So this is what we kind of did. This was the very first Hoodie table. We killed this. This is anyway, not something that we like to use. We just logged the changes from Kafka into HDFS, just as a staging area, and essentially we used this change log to simply upsert. We built basically the Hoodie upsert library. Basically we built Hoodie, through which we are able to upsert the trips table at say 30 minutes using 100 executors based on what we are using, instead of 500 executors running for 6 hours. And then we replaced this guy with an incremental pull, which we also implemented inside the Hoodie, which just takes 2 minutes to pull the entire change in the last 1 hour. This is again this is just done by some extra metadata tracking. So we track the files that have been touched since a given time stamp. So if you want to find out, okay, give me all the trips in this table which have changed in the last 1 hour. You don't have to scan the entire table. You simply can, use incremental pull. It will just give you the new or the updated rows. Then again, you can keep chaining the upsert to update whatever you are computing downstream, and that essentially is bringing, turning all these things into from an approximation to like it's more accurate, because we are exactly giving you every row that has changed since a point in time. So yeah, this is we saved a lot of resources, and the side effect is latency going down. So those two go hand in hand, because in this ecosystem all you do is read and write data, right? And anytime you cut down these things, the efficiency will all improve. So this essentially is, as you can see, the database ingestion is the motivating sort of use case for us to build this, but the concepts around Hoodie go a little bit deeper. So let's start, on a fresh slate. Let's think about, okay, a data pipeline. What are we usually doing here? Mostly what we're doing is we have a source, we have a sink, we have a pipeline in between to transform this data from the source to the sink based on your transformation, right? And these transformations are either projections, filtering, or aggregations, windowing, very common in streaming systems, and joins. And then usually you have three levers for any pipeline or transformation, which is latency, completeness, and cost. Latency is the time taken to actually run the pipeline. Completeness is how complete is your result or how correct is your computation. And then cost is how much cost are you willing to spend to get a certain amount of latency and completeness. So typically the world you pick two. I'll give you an example. If you take the standard Lambda architecture, the streaming layer usually has access to record level updates, things like that. But when it gets to joins and windowing, and even in some cases even normal projections, it tends to favor latency more than completeness in a lot of cases. You can try to achieve higher levels of latency and completeness by having like maybe more cost thrown at the problem. But anytime you are say joining 7 or 5-6 streams together, your completeness is going to take a hit if you want the latency also to be very low, right? So does that make sense? Or okay. So overall, the batch layer, it basically says, I'm going to take a hit on the latency, but I want to ensure very complete results, and I want to do it in a cost-efficient way. So what we see here is there's an artificial dichotomy where you're forced to choose a set of tools with a set of constraints, and that's how most of us have been operating, right? For us, say one of the primary use cases, as you'll see here, is for us it was like a spectrum. There was not a very clear dichotomy. If you plot latency and completeness against each other, we do have a lot of good streaming use cases where it's worth it to spend the extra cost to get the latency, right? Like dashboards, or you're extracting features from streams as you go, and you're trying to give an output signal back into the real world, like you're trying to predict ETA, things like that, right? And there are lots of, and these things sometimes take a hit on the completeness, right? Because there could be late arriving data, whatnot, which can mess with your completeness. But you have, say for fraud, if you're detecting fraud, maybe it's good enough that you have 70% of the data to gauge, generally fingerprint what's going on, right? So if you take batch use cases that typically highly complete and highly latent, like experimentation, okay, give me a scorecard for all the experiments that we are running, backfill pipelines, data science sort of work, and feature extraction. So if I want to have a machine learning model built based on the 30-day, trailing average, blah, 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 so that those all become batch. So for us, the interesting thing was we had these kind of use cases in between, which is fraud detection, but a lot more deeper. We want to kind of crunch a lot more signals to basically detect what was going on, and we wanted a faster turnaround time. This is akin to kind of updating your fraud coefficients at a much faster pace. In payments, like, okay, what is going on in the real world? Do we need to adjust any incentives that we are running? Kind of generally more like a health check on our incentives that are running, and flag cases where the equation has changed in the world because some event happened or whatnot, right? And faster ETL. So like raw data in a lot of cases is a little bit uncooked and not very easy to consume. We would also like the faster, the derived tables to be faster without compromising on the clean architecture of the data lake, which is have operational or raw data, don't transform before you ingest. And when you transform later, it adds latency. So we try to see if we can use all of this to bring the latency back to like an hour for most of these use cases, right? So this is what we saw, where you can look at all of these as simply like data pipelines, which just have varying degrees of completeness, latency, and cost benefits to it. So, and overall, the other thing is, the common question I get asked is, why don't you make everything streaming? And the real answer is we cannot, because there are typically 100x more batch pipelines than streaming pipelines. So we have tens of streaming pipelines, maybe, but we have 100,000 plus queries or like pipelines that are running in the batch mode. So it's just not an option to make everything streaming without paying a prohibitively high cost. So like, what do we then mean by incremental processing, right? So essentially, we're still running batch pipelines, except they are mini batch pipelines, and they provide higher completeness than streaming pipelines by providing multi-table joins. If you try to join multiple streams in a streaming job, you'll like realize how hard is it to actually align the streams together. But if you do it in a mini batch pipeline, you can gain higher completeness than what you'd get from like a streaming job, right? But they do it with streaming primitives or in streaming fashion. What I mean is, typically a batch pipeline just either bulk recomputes and then writes the result back, right? But we have, by adding like streaming primitives, we can provide lower latency than your typical batch pipeline, because we are only consuming new input. Going back to the example of how incremental pull, you're only consuming the new trips that are coming in. And we have, with updates, we have the ability to update old results, right? This is very streaming like, just like how you would write a Flink job or a Storm job or consume from Kafka, where you are only consuming new events, and then you would use like a key value store to accumulate your counts. So it just provides like lower latency than a batch pipeline just by doing the primitives. So we don't move the data to streaming, but we just brought the primitives back to batch. So quickly, why do we do this? Increase efficiency. If you can see, if you want to simply count the number of events that happen in 10 minutes, if you keep doing a stream processing job, you have a result store, you keep doing it always, so you're doing 6 million updates at this rate, right? If you simply run a mini batch job and all you want is a latency of 15 minutes, you can simply run a batch job every 5 minutes, and it's going to do just one update, or it's going to amortize all those I/O that you are even doing to your key value store, right? So this is much less I/O, and you get to do on-demand resource allocation, where you don't have containers running all the time. So there are lots of use cases in the spectrum that we saw before, which can benefit from mini batch jobs. The other thing is, we do this, there is a lot of good Hadoop SQL engines which are a lot more mature, like we saw before. We get columnar file formats, and we get good support for joins, and we are able to cover a wide range of use cases already. And overall, we are able to like simplify our architecture, right? So you just run so This table, for example, is a more complicated ETL table where that is your primary ingested raw trips table. Then you're joining it 2 times with 2 other tables, and you want to, all this is doing is something like currency standardization. So if trips get reported in local currency, then it's just converting everything to say USD, something like that, right? For this, you need not run a streaming system. You can simply use the incremental pull or incremental consumption on that side to just get the change log, like join, and then do an upsert on the other table. The whole pipeline will finish in like an hour, which you don't really need to use streaming for. So all this, like I keep saying, consolidates very nicely into 2 primitives, which is an upsert. It's like state stores and stream processing, helps you modify your process result, and then a log of an incremental pull, which just gives you a log of changes that avoids costly scans. This lets you keep chaining these Hoodie datasets and build like kind of incremental DAGs to run your data pipelines. So finally, like formally introduce Hoodie. Hoodie stands for Hadoop Upserts and Incrementals. It's essentially a storage abstraction to apply mutations and again pull changes. It's a Spark library, so it scales horizontally like any other job. It stores data set directly on HDFS, so there is no storage server or anything that you run extra. And it's open source. It's here, lives in Uber Hoodie, and then there's a blog post where we covered a lot of the design aspects of Hoodie, which are also covered in this talk. So high level, what you do is you have a change log, you have a Spark program, which is going to upsert this, then it's just going to behave like a normal table that you query via Hive, Spark, and Presto. Additionally, you can also pull a change log out of it through the same Hive, Spark, Presto agents. 10,000 feet, you embed, like you pull a Maven dependency into your Spark job, you instantiate something called the Hoodie write client, and then when you do upsert, it just stores and indexes the data set on HDFS. There are 3 major components. One is the index that helps us map between, to do upsert, we need to know which files a given key is present in. So the index provides that information. The data files are the actual Parquet data that we are like managing. And timeline metadata essentially tracks all the operations that are happening on a Hoodie data set. So it's kind of like a redo or a commit log where this is what is used by, say, query engines to look up what commit is valid, blah, 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 and then like read the data files. So we have 2 major concepts that we'll organize our deep dive section by. One is the storage type and the view. So storage type is the set of algorithms that we pick to index the data and organize the data files. So how you write data into a data set is controlled by the storage type that you're using. And once you have a given storage type, then you have multiple views on the same data. So for example, in the previous slide, as you saw, the normal queries is one view, and the incremental data that you're pulling is another view. So views simply are a way in which you use a combination of timeline metadata, the index, and the data files to actually serve your queries out. Right? So to get like super real, this is how it actually looks like. So this is how you ingest like some input data as which is present as a Hoodie record RBD, which is essentially some metadata with a Avro payload. So you have the config object, you give it the path at which you want to write it, give a schema in which you want to organize your table by, give it parallelism, configure the index. In this case, we are using the Bloom index that comes built in with Hoodie. Then you set compaction settings, whatnot, and then you make the config, And then once you have transformed your input, be JSON file, CSV, whatnot, into a Java RDD of Hoodie records, you instantiate a write client with the supplied config, and then you call client.upsert with a given commit time. A commit time is a key concept. You can think of it basically as a timestamp at which you are writing data into a data set. And once you write it, it gives you a write state, like an RDD of write status back. This lets you examine for failures, and if you decide to commit it, you can say client.commit and pass in the same kind of commit time. And then otherwise you can say client.rollback. So this effectively is how you say update a given data set that is stored at path with new records from your source, essentially. So what happens is this runs like a DAG like this. So essentially this part is like our ingest job, figuring out what files to run. Then we do the index lookup. The actual writing of the data happens, and then we commit. So, like I said before, all of this runs just as a Spark job on your cluster. So, once I have this, there is a Hoodie Hive utility, Hive sync tool, which will basically look at, essentially keep the Hive metadata updated with whatever you written on your data set. So once you have it, for example, using Spark SQL, you can query the same data set so right now we have, say, Spark SQL supported out of the box. You can just query it like a normal table. This is a work in progress, which is supporting like a data source, where you can read and write from Hoodie datasets natively using Spark. So I hope at this point we generally, everyone's on the same page on what the primitives are, our general motivation, or what's the project really feel like. If anyone is like completely not on the same page, please let me know. I can clarify a little bit before I go into deep dive.
Quick question. You said it's looks like you have a commit. Is that supporting the asset transactions?
Are you talking about Hive asset transaction project?
Yeah. Is that? I saw your code has like a commit or etc. So is that the kind of asset transactions?
No. So that is all that's not implemented on top of Hive transactions. If that's what you're asking, this is Hoodie's own primitive.
So it's Hoodie's asset transaction.
Yeah. Okay. So we have no dependency on Hive asset.
Okay, but my other question would be like the content is storing on HDFS, right?
Correct.
I mean, just curious, how do you update? I mean, it's an append-only process.
Yeah. So that's the deep dive.
Oh.
That's the deep. So we'll tell you what exactly is the commit metadata, how we do this, and at the end, comparison section. I'll also talk about Hive transactions and what's the difference between Hoodie and that project.
Okay, that's interesting.
Cool.
Thank you.
But generally, we are on the same page. Sorry.
If you have multiple clients that want to update the same data set, can they run in parallel, or they have to be serialized?
No. So Hoodie is a single writer, multiple reader. You can use something like Apache Curator and coordinate out of band. We don't have it added in. So the very key design choice between, say, something like Hive, while we're on the topic, Hive Asset and Hoodie's MVCC system. We don't have concurrency locking, or like we don't actually try to do database style asset transactions. Most of analytics, what we've seen is a single writer use case in a lot of cases. So that's what we support today. Cool. All right. Sorry.
So, what's really happening in case of rollback?
Sorry?
I saw a rollback also.
Oh, okay.
So, usually it is one side. It's open mode, pretty much touch base on the very new rollback. What is happening underneath?
So underneath we basically don't publish. So essentially the commit is a file that signals to the query that this is a valid, this data is valid. So we rely on the HDFS name node's atomic rename to implement that. So rollback would mean no one would see the data, and we would actually roll back any effects of the commit from the data set. So that the typical use case for something like that is you want to inspect the failure and say there's a schema merge error that's happening across the board. You want to then pass the pipeline alert and have someone take a look at it, if that's the problem.
So when you have many sources of same information, sometimes you have data quality process that is running as part of integration, and you resolve inconsistent information from different sources within that process. This, what does this, I'm sure you have this kind of situation as well. So did that become problematic with this kind of incremental pipeline? Does that get pushed out further downstream quality process?
Actually, no. So all of the quality processes are built into the ingestion system. Hoodie is a component of the ingestion system. So what the ingestion system at Uber does is things like we keep counting Kafka messages at every hop, and we make sure, like with Spark accumulators and things like that, that like all the data made its way into it. And if there is a schema mismatch, we log to a separate table so someone can fix it and come back and replay the data and all. So the fact that we have incremental consumption does not change anything about the data quality issues. They're actually orthogonal to each other.
Okay, in fact, would quality processes become Hoodie clients in this sense?
Correct. So we do have some cases like that where they look at not the data, but they look at the commit metadata to say, okay, have I written enough records to each partition? So we do have use cases like that, but most derived, say, ETL jobs just consume the incremental, put it onto their real store, and then run quality checks on that. Because at that point, the quality check is not on whether we are able to incrementally consume or upsert. It's more like the business transformation. If we use the wrong join key, then it's going to be wrong, right? Whether or not we use Hoodie.
Talk with you offline.
Okay, cool. All right, sweet. So with this, I think we can go into the guts of what we do. All right. So as I said, we'll mostly organize the section in terms of storage types and views. So storage type again is how the data is stored, and views is how the data is read. So we have two storage types. One is called copy and write, which essentially just versions files. And then the second one that we are actively productionizing right now is merge and read, which is a more real-time version of this, where so copy and write, when we designed it originally, we did not want to take any hit on the query performance. So the design goal was, hey, we want the query performance to be exactly the same, just the ingest latencies to go down by a lot. So we took all the hit on the write, and that is copy and write. And then merge and read, there are more levers to this, where we have a compactor. It feels more like Hashbase and like some of these key value stores that you might be familiar with. And so on these storage types, on copy and write, we support two views for looking at the data that's in the data set, which is a read optimized view, which is the normal queries, and then a log view, which gives you the incremental. So for example, if you do select count star from trips where date string equal to blah, which is your high partition, that's a read optimized normal view. Then if you want to, you have a special tool, like special variable that you want to set in a Hive session, then if you run the same query, even without the date string, it will simply give you the incrementals or the log view. So with merge and read, we added an extra view, which is a real-time view, where we essentially ingest as quickly as possible and present the queries with a merged view of the data that's in, say, Parquet, a columnar format, and this Avro row-based format. And again, so this is not to be confused with Hive views. This is just a logical explanation. All of these are Hive tables. Basically, these are all registered as separate Hive tables, so you can go query this and you'll get the corresponding view of the data. Sweet, so storage. So first we'll look at storage and then go over all concepts here. Consider a Hoodie data set, which is organized by dates. We are beginning with your very familiar Parquet dataset. Usually you have a bunch of Parquet files lying around here. This is all like registered into Hive, whatnot. Now we have 200 GB to ingest, and we are running this job every 30 minutes. So what we do in copy and write is essentially we've added an extra index like a Bloom filters and ranges to the Parquet file. Then we use that to identify these, among these records, which files within this partition have to change. So this is like a a partition with like a lot of files. Then all we do is there is file 1 v1.parquet originally. Assume there were some records within file 1 v1 that actually changed. Then we simply rewrite the entire file. So basically, again, going back to what I was saying before, the idea here is queries simply filter metadata and run the entire query on purely columnar data. So there is no performance hit of any sort on this data set, on this type of storage. So rough math, we do this for trip data set that we showed before, 1,800 odd partitions, 100 GB partitions. Again, the other thing we do is block align files. So you end up with 800 files, you have this much of a skew, then you have 7,500 files rewritten. It takes 20 seconds to rewrite a 128 MB file, and with 100 executors, you finish in 24 minutes. That's basically what we saw before. Right? And this is copy and write. It's like really simple. All it does is adds an index to Parquet and then simply rewrites the file. And then this was hugely helpful for us as we moved all three major query engines to this new storage format and without any kind of downtime or major incidents. So next gen that we are pushing on now is, hey, let's ingest more quickly, right? So let's actually ingest smaller amount of data in smaller amount of time, right? Because the thing there is with the previous copy and write storage, there is only a limit to which you can push this. You're bounded by how long it takes to rewrite a file. And again, going back to our cost, whatever those things before, you have to throw a lot of hardware for it to make it go much lower, right? So we wanted to provide multiple levers and make people choose between whether you want fresher data at a little bit more query performance, or do you want to keep your pure columnar performance but like tolerate higher latency, right? So what we did was we added a log file additionally to every file that we wrote. So new records just get logged here. That's it, right? And then when there is enough log that piles up, so we have a cost-based compactor which basically looks at, hey, you have 128 MB of Parquet and 128 MB of log, so it's time to compact. So then it basically does the same thing, which is rewrite the file as a new version, except now you waited a little bit, so you get to amortize the cost of the rewrite over time, right? And we have next batch, again, gets logged to the latest version, and then when this fills up, you are going to compact this again. So with this, we are simply doing a lot of new files in every batch. We just have like say 8 new files, and we can even run it in like 10 executors, except for when the compactor kicks in, and it just takes 2 minutes to write. The catch here is the compactor, right? So what are we losing? So practically this works out. I'll tell you why. Because a lot of data sets, you have small updates to like old data. So in this model, we'll simply log them and then walk away. If you think about it, the query hit on those data sets won't be that high, right? The cost that we were spending before to rewrite a file, even if a single key got changed, is now basically amortized over time, and that's the kind of trick here. If this does seem tricky, it's very basic stuff. So index and storage. Index, the goal of the index component is to tag the ingested record as either an update or an insert. It uses a combination of Bloom filter. We also built one which uses HBase to simply store the record key. It has advantages and disadvantages. It is probably quicker, but again you need a really good HBase infrastructure. And if HBase and HDFS dataset don't agree, if they go out of whack, say there is an HBase outage and you lose a region server and something happened, then yeah, you need to be able to do all the repairs and like. So we try to keep things consistent. We just stuck with the Bloom filter index because it is very consistent with the file itself. So storage, it can store data on HDFS or compatible file system or cloud storage. So we have people successfully using this on Google Cloud. It works on S3 too. With S3, the thing is, it's not a problem that Hoodie introduces, but Hoodie has timeline consistency, as you can see, but S3 has eventual consistency. So we need to build something in between to kind of tell the queries when you can really incrementally pull whether the files have become stable. So that part is, I think, something we'll work on. But as it is, it doesn't like make it any worse than what it is on S3. So overall, we have two file formats, which is like Apache Parquet for read optimized performance, and we have Apache Avro for write optimized. So we can just we simply read from a Kafka feed and then append to Avro. That gives us like really good ingest latency. Concurrency, so we have multi-row atomicity. So that's the other key thing that we wanted. So if you play with things like HBase, or key value stores, I have a batch of data I want to ingest, then if it fails in between, you have to go and roll back with a partial effects yourself, or design a TTL mechanism or whatnot to do it, right? So this is something that we wanted to build out. So there's a single commit. All records that are committed as a part of that commit are there atomically present to queries. And it has strong consistency as long as you're using something like HDFS or GCS, which is strongly consistent. Single writer, multiple consumer, and we have MVCC for isolation. So there is the other thing is locking on locking between query and writer. So more than the writers locking or contending on each other, we never wanted the query to be blocked by the writing process. So they can run concurrently to ingestion, which is definitely needed. So the other thing that we had we spent a lot of time on in our Bloom index implementation is skew. So we have a lot of skew in a lot of data sets in different shapes. So you can either have a lot of records going into a few partitions, or like what we saw before, fewer number of records spreading across hundreds of partitions. So Spark has this problem where if you try to shuffle more than 2 GB in a partition, it kind of explodes. So for us, if we have to land this in production for so many data sets, we want something that can automatically partition. And so Hoodie basically uses statistics in the input data to automatically compute partitioning for the joins, and gets rid of stragglers and make sure the DAG is balanced. And yeah, then compaction. So again, this is more for the merge and read storage. So it's essential for query performance. Like I was saying before at the start, if we kept logging and merging all the time, the log would grow indefinitely. Every query will have to read an increasingly higher amount of data. So compaction right now is scheduled asynchronously, can be scheduled asynchronously to ingestion. Although, to be honest, we have not fully done that in production yet. But thanks to MVCC, this is doable. And ingestion basically locks down the files that are going to compact so that no one else touches this. and we have pluggable strategies to prioritize compactions. Like for example, some people want the recent partitions to be compacted first. Some people want to go by whichever has the largest, log file basically. So failure recovery, again, this is one benefit of actually relying on Spark. All of the failure recovery, distribution, all of that comes for free, thanks to RDDs. There are no partial writes, and we can roll back specific commits. That's pretty much all the storage concepts. So I'd like to talk a little bit about views. Okay. So, like I said, there are three logical views. So if you plot query execution time against latency, the read optimized is really good at query execution, but has a lot more like data latency. The real time probably is on the other side, which is it has really good data freshness for your ingest, but you may have to trade off you're doing the merge on runtime on the query side, so it's going to your queries are going to cost a little more. Then we have a special view, which is it uses the timeline information to simply pull records out and just give you like the tail of the data set. So this is how views see the same data set that we saw before, right? So copy and write. So so the read optimized table, right? It won't even try to read the log file. All it will do is it will just run the query on the latest Parquet file and be done with it. So, but the real-time table is going to read the Parquet file and its corresponding log file, try to merge both and give you the latest result. The incremental log simply has metadata to track these changed segments. So we use a combination of a log and pushing predicates into each Parquet file to efficiently pull out the change data. So all of this is implemented as input formats, so which is like a standard integration point to Hive, Presto, and Spark. Presto did not respect input formats, but we added a change into Presto to make sure it calls the input format hooks for the Hoodie tables. Yeah, this pretty much is our read optimized, copy and write performance on Presto. This is what we set out to, which is on par with a raw Parquet dataset and a Hoodie dataset that is built on using copy and write. I think this we covered. Okay, so the one thing I want to point out is every Hoodie dataset gets a bunch of metadata columns that are registered into Hive. So one of them is Hoodie commit time, others being like record key, things like that. So the Hoodie commit time effectively is the kind of the arrival time. If you are like familiar with Tyler Akudu's streaming on O1 blogs, if you read those, so the date string is your processing time or your event time, and Hoodie commit time is a standard arrival time that you get for every table that or data set that you build with Hoodie. And the incremental log view just builds like a very fast way to issue a query such as this, which is to say, give me new data. So use cases. The primary use case like that we saw is near real-time ingestion. So you have online stores from which you want to replicate the data. So you can use this to get data in like say 10 minutes, and then you can drive a lot of your analytics on this. So this essentially means you have more budget to kind of do more streaming or real-time use cases. So incremental data pipeline. So once you ingested the data, you can use the the incremental primitives and the tools that we ship in Hoodie to like build incremental data pipelines, such as the ETL pipeline that we saw before, something like this. join database against Kafka, join and like have a Hoodie model or a derived table. And overall, I think you can, in some cases, this is more philosophical, which is, so Hadoop is still like synonymous with the big data, right? So if your latency tolerable is in this range, you can eliminate in a lot of cases your specialized serving layer, and you can simply have data that you're ingesting anyway into HDFS be directly serve more of this too. So yeah, in this world, for a lot of use cases, you can simply ingest the change set into a Hoodie table. Then if you have a change log stored somewhere, you can reprocess and do this. In basically a same unified storage, basically analytical storage. So at Uber, we have, like I said before, most of our ingestion have been moved into Hoodie. We are ingesting every 30 minutes right now, and we're moving towards the 10 minutes. We are kind of in dark, like we're shadowing right now. So I think in the next few months we'll like switch turn the switches on. And we have a lot of incremental ETLs for a bunch of these tables which needed updates. And so far we've been able to reduce resource usage across a lot of our big tables. And so if you see this data, the little data set here, it's only 0.4. This is a data set which has very high write amplification, something that benefits a lot from the merge and read project. So, okay, so this is the hard part, which is, okay, we picked some trade-offs in the system. How does it compare against others, right? So I would like to, before we go into this and I talk about some stuff, just try to get everyone up to speed with this benchmark that CERN recently published on around analytical formats, right? So the bet here always for scans, as you can see, like I was saying before, HBase performs really poorly in terms of scans compared to like something like Parquet. And so something like Kudu is catching up, but it is still, Parquet is the best in class columnar performance, if that's what you want. In terms of write rate though, this is again a point that I was making before, which is about, hey, you want to run HBase for primary analytical queries, then you need to be able to scale HBase up to the levels of HDFS, right? So if you see here, the write rate for all systems which are kind of storage systems drops off by a lot because you have RPC overhead and whatnot, right? So if you see Avro, you can write much faster, and then Parquet is still like much higher than something like HBase or Kudu. So what we try to do, our trade-offs are, okay, keep the Parquet columnar performance, try to mask the write rate, and just build these primitives in between that help you do a lot of what these systems try to do already. So this is, I try to contrast Hoodie with the two other systems that we get most questions about in terms of a number of factors, right? So so these two systems I have a lot of respect for, but I feel in some cases we are in handling slightly different problems. So write latency, HBase is a really it's basically a really good OLTP store. So it's going to give you milliseconds of latency for writes, right? Kudu I think is more Kafka-ish from what I've played with. So again, I have not run Kudu in production, so I don't know. But it feels like something like streaming latencies at seconds. Hoodie right now sits with 5-minute update, 1-minute insert ballpark. We feel again, like I said, there's so many batch use cases out there which can be sped up with this already. So we are very happy to just help with those use cases and make them more efficient at this point. So our North Star would be for write latency to be as close to say something like Spark streaming, because it naturally is extensible since Hoodie is also built completely on Spark. So scan performance is not optimal as we saw before. Kudu has its own columnar format, and Hoodie relies on state-of-the-art Hadoop formats. We don't try to invent file formats. Query engines, Headspace probably has a Hive connector, no Presto support. And Kudu, I think it has good integration with Impala. Spark, I've heard, but I'm not so sure. But Hoodie, for us, we had this integrated into Hive, Presto, Spark at scale across our entire production cluster for the past few months. So deployment, again, so HBase needs a bunch of stateless region servers that you need to manage, scale, and be able to take care of in addition to your HDFS data nodes. Kudu actually completely departs from HDFS. You need your own SSD hardware with specialized storage for it to actually, the trade-offs that are made to actually, bear fruit. Hoodie is just ways like a Spark job running on YARN or Mesos talking to your HDFS or GCS or your cloud storage. Okay? So it's basically a shared storage system than being a specialized storage server. But nonetheless, there are three things which we have built in Hoodie based on our use cases, which I think are not in the other systems, which is multi-row commit rollback. So we can do this. Incremental pull. So Hoodie has been from day one designed with incremental pulling also. That's another thing that's it differentiates it from something like Hive Asset. Is we're not only interested in simply updating, but we want to be the abstraction that will let you chain these DAGs together. And then we do things like automatic hotspot handling. So anyone who's operated a database knows how hard is it to kind of operate it and make sure with the workload you don't have skews or hotspots in your cluster. Hoodie is open source. We have Shopify who have, I think this is an old slide, they're close to having their first pipeline, and they're using it for GCS, database ingestion. We have a few companies like DoubleVerify, Pinterest, Netflix, which who have, including GoPro, who are in this kind of a yearly phase where, hey, looks interesting, we want to try it out kind of phase. But yeah, so engage with us on GitHub Hoodie. There is a issue there actually. If you like to be added to a Slack channel, that's fine too. Try out our utilities. We have a few utilities to sync Hoodie datasets into Hive, or a Delta streamer tool, which essentially can read from Kafka or tail a folder on cloud storage or HDFS and ingest it as Hoodie. Yeah, Uber is hiring for Hoodie, so if you're interested, ping me too. Future plans, merge and read is our top priority. So getting this right is actually one of the reasons why we have not invested super hard on making it very developer facing. So we want to make sure this is done, the right abstractions are there before we start, adding on things like data source, and just want to make sure we have the right abstractions. Right? Then we have a global index project. So this is a slightly tricky thing. I think it feeds into the data quality sort of issues. In some cases, the partitioning field changes. So right now, our indexes assume that you know both the key and the partition to which it belongs to. So global index is a project to build index which can map a given ID into without relying anything about its partition path or the partition to which it belongs to. Like I said, Spark data source and Presto plugins. So Spark, we basically want to do something like this very, very easily via Spark SQL in a pipeline. Essentially, if you say var Hoodie commit time greater than something, then you can actually build a lot of these pipelines in a more understandable way. And thanks to it being MVCC and commits, it's very replayable. So we usually keep up to 24 hours worth of commits on Hoodie. So if there's any problem, we can go back and do point-in-time queries and kind of understand what's happening. Beam. So this is the grand goal, which is so Beam today, if you know, is a data pipeline abstraction. So the idea is if we can have a Hoodie IO in Beam, which can simply fill this gap between streaming and batch, then we can actually have Beam to express a pipeline and just run it either in this mini batch sort of mode or a full-on streaming mode on something like Flink, or like a batch on something like MapReduce or Spark seamlessly. So these are more developer-facing projects, which I think will get prioritized more and more as we go forward. But I think I at least owe Chester the data source, which will get done. Takeaways, I think we feel like this was a big void in the Hadoop land. It plays well with the existing ecosystems. So the clear choice we made here was to leverage Spark more versus reinventing another storage silo. If you start down this road of writing a storage server, then scale it, then you have to it's basically we feel like we'll fall into the same trap of the write rate graph that we saw before. And it's designed for incremental processing. So, incremental pool is something that we think we've only added it to Hoodie. I don't think any other project out there has this. That's pretty much it.
Great, thank you. Any questions?
So you mentioned there are two types of data. One type is coming in for today, and there's another type of data coming in for historical records. So I think you focused on the historical record, which is more of a random I/O accessing pattern. However, you still have the large amount of data for today, as Uber, a lot of people are using all the data today. That is more of a hard partition type of accessing pattern. So is Hoodie, this kind of incremental processing, still suitable for this hard partition accessing pattern? Or is we have the old historical random I/O accessing using Hoodie and the hard partition accessing using like micro mini batch or aggregated commit?
Okay, so let me try to understand the question a little bit more. So is your question, is Hoodie gonna solve like real-time query problems on like fresh data, or?
I think it's because of you have so much data that goes so back into your partitions.
Okay.
That has a significant cost to your online processing system, which you build Hoodie to minimize the cost. However, on the other side is you have so much data that are accessing today, this one partition. Is Hoodie still suitable for this kind of accessing model?
I see. So, okay, I think what you're saying is if the access pattern is heavily say today, right? So actually, it's more a factor of the amount of data than the partition. So we have use cases where a single partition in a highly big Kafka topic has 2 terabytes, right? So the same call, if you have to update that, without something like Hoodie, you have to rewrite the partition. So that is rewriting 2 terabytes. But if you use something like this, you'll probably end up writing way less. And also on the incremental consumption side, you still want to consume that Kafka topic and do a Spark job downstream. You still get the benefits of incremental consumption. So it's more like a factor of the data size than this. Like if you, for example, your hard data, today's data is only 100 GB, right? And or say 10 GB, I don't know how much benefit you will see, right? Because the full scan itself will only take like short amount of time. Does it answer your question?
Yes, thank you.
So my question is regarding the merchant read operation that you are planning to do. So why don't we just always support or always give to the user the last available version of the record that you have? I mean, only to there is some Boolean structure, you could be just having like an index pointing to the latest keys, and then just use that way to all the latest blocks that contain the keys that the user wants, and then just give that to the user.
So the merge and read, the query does see the latest data all the time. So what I described is what goes on between. So the merge between say the log and the columnar data is something that the Hoodie library will take care of. So the user is always presented with the merged latest snapshot of the data.
So merging read, you mean merging the log structure data and the Parquet data?
Correct, correct. So what we did was we just provide different views of the same physical data set as like different tables. So there will be like, if you go back to, let me try, give me 1 sec.
I thought you were actually merging the records, like merging the versions of the records, but you were not doing that.
Yeah. So if you see this, there is a Hoodie trips RT table that we also register. If you query this guy, it will under the hood it will merge the log and the Parquet data and then hand you the latest fare for that trip person. But if you query using the read optimized table, then it gives you basically what's in the latest Parquet file. Does that make sense?
In the latest Parquet file, or when you use the merging read, it will give you the latest Parquet and the log.
Sorry?
When it's the latest commit, it will give you the latest Parquet and the log structure data sets.
Sorry, I'm not following.
And then you have a diagram. So show in the diagram, you have different views, and that I think I'll have to consider.
Okay.
So no, what I was saying is, so when you ask for the last commit version, it will give you the last Parquet file plus the data that is on the log file, right?
So when you say the last commit version, so can you describe your query? I think that's where the
Select start from table where commit ID is the trace.
okay. So I think what you're talking about is like an incremental query, or
No, I just want to see the latest data.
you just want to see the latest data. So then you don't have to include commit time or anything.
Okay.
You simply say select. I think the internet stopped working. Yeah, so you don't have to include anything like commit time or anything. So you simply query the table like normal, right? What I'm trying to say is if the table is a RO table, which is like a read optimized table, so basics is you ingest once, you get 2 tables in hide. One is the read optimized table, the other one is the real time table, right? They are registered with different hooks to intercept your query. So that when you do the same query on the read optimized table, it will look at the timeline metadata, find out what the latest commit is, and then go to the latest Parquet file that was written as of that commit, and then simply execute the query on that data and then return you the result. If you go to the real time table, it will do the same thing, but additionally it will merge the Parquet file with the log data that we've logged as a delta to that Parquet and give you the latest value as of that time. Does that make sense?
Yeah, that's
Okay.
Does your real-time view span all of the Parquet files in history, or is there like a window limit?
No window limits. It's basically whatever your query hits, whatever partition your query hits, it will go to the same.
Do you merge on time or you merge on the file size? Like logs needs to reach some size before you merge, or you merge them only like one at least once?
We have two both strategies. What we actually do is merge on size. We pick the log file Parquet file combination that has the highest ratio.
Right, but for example, once in a while you update entries at 2 years old,
Mm.
and it's once in a very rare event. In this case, that log file may exist forever.
Correct. It can. So there's a parameter which says this is the amount of I/O I'm willing to do for every ingest, and Hoodie basically takes that I/O and then picks the most uncompacted files. So in this case, yeah, it will remain uncompacted for a long time.
I think the slides are not working.
Yeah.
But there was a slide comparison.
Hmm?
That first column was HBase, the second one was Hoodoo, the third one was Hoodie.
Correct.
the first one, the query engine, there was a column,
Sorry?
the HBase column
Uh-huh.
in the row of query engine.
Okay.
The entry was high.
Correct.
I'm wondering why not put a spot connector in there? The spot is now up to HBase directly and act as a query engine.
Correct. But I don't know if it can do it through the Hive table.
It is.
It is.
Yeah.
Then you're right. This then should say
So
Hive and Spot.
that's exactly my point. The performance is very high because Spark is understanding the schema and can write and read, so it can do both. So the file is fully read.
Correct, but I think still it doesn't change the fact that HBase is not like your analytical columnar format, right?
Right, just because you went in the Parquet direction.
Sorry?
You went in the Parquet direction, but if the entire data set is in columnar format, the HBase still can do.
No, right? This is like an independent benchmark. If you see like, you can clearly see a scan performance on HBase generally is not great. This is actually one of the motivating reasons to even build Kudu. If you read the Kudu paper, this is the primary reason. HBase, end of the day, is still a OLTP, database. So it's really great for time series data, like if you're doing OpenTSP style monitoring use cases, it's really good for. But if you're doing large queries with like rollups and all of that, then the RPC, you keep scanning a lot, and that usually kills you a lot more.
What kind of data set used for this benchmark?
I think it's their data set. So you can just Google CERN blog on analytical.
How do you separate log file from a Parquet file? Are they separate by naming convention, or you store them on a different partition?
It's in the same partition. It's just .avro.version instead of .parquet. But it's the same. They share the same file prefix.
Some prefix. And somehow you instruct create table to not to include those. When you're building a view, you have to.
Correct. So we register these as external tables. So all we need is just the external, like the partitioning information, and basically the latest schema from the log file to be able to sync it back into Hive. So if you get a new column in the stream, you want the Hive table to reflect the new column. So those kinds of things we need. That's pretty much what we use the Hive metastructure for.
And are you planning to tackle the problem of schema evolution?
Yes. So whatever Avro and Parquet do, we do. Basically, that's a short answer, but essentially, as you see in the right client code, we do have a schema fixed. So, and then at Uber, we have a system that ensures you can only produce data with backwards compatible schema. So if you add, basic Avro backwards compatibility rules, if you follow, yeah, you'll be able to merge and evolve your schema.
Other questions? All right, thank you very much.
Thank you.
Thank you for coming.